This is the Chapter 9 outline on significance tests. And we're determining when can we determine that a sample statistic is too unlikely to justify a claim. So when can we say our sample statistic is far enough away from what somebody claims so that it couldn't possibly be true? And to determine how likely it is we would get a test statistic or our sample statistic that we do, given that the claim is true, we use a p-value to determine how likely it is that that would occur. Why do we reject a null hypothesis when we have a small enough p-value? Why do we fail to reject a null hypothesis and not accept it? And those are going to be things to think about as we go into significance tests. Let's talk about what do we mean by significance tests and how does it compare to a confidence interval. So here we're starting with a claim as opposed to a sample statistic. So in that way it's different than confidence intervals. So if our claim is true, so that's represented by the proportion from our null hypothesis. We use this little subscript, the little sub-zero, to represent our null hypothesis. So we're saying that this claim is true, that the true proportion is 0.5. If that's the case, then we would tend to get values that are close to 0.5 and not tend to get values that are very far away from 0.5. Now in the past chapter we used p-hat to make a confidence interval by adding a number of standard deviations times the standard error to get this margin of error above p-hat and below p-hat. Now you can see this confidence interval captures the true proportion if this true proportion were actually true. So we would capture it here, whereas a sample statistic here does not capture it. So with a significance test, what we're saying is if this parameter is true, so we assume that the claim is true, 0.5, then our values would have a normal curve centered around it. Now if p-hat is, if our sample statistic isn't that far away, so if p-hat's here, we're saying, okay, that's plausible that this is still true, and just by chance I got a sample proportion that was under the claim. Or by chance I got a sample proportion here that is over the claim at about 1 standard deviation above the claim. However, what we're saying is if my sample statistic, if I make my claim that it's 0.5, like let's say that I have 50% of the vote for governor of California, and we get a sample statistic that's up here, much higher than it, then we can say it's clear that that claim, that this sample statistic would not be very likely to occur if the true value is 0.5, meaning it's so much higher that we have evidence against the claim. And that's what a significance test is testing. Is our sample statistic far away from the hypothesis, what we're saying is true, so far that we can claim that this hypothesis is not true? So in the case of a p-hat here, we would reject. These shaded regions represent rejection regions. Now here the alternative hypothesis would be that the true proportion is not 0.5. And if we got a p-hat down here in this area or up here in this area, we would be saying that we'd reject the null hypothesis that the true proportion is 0.5. Because it's shaded on both sides here, this is a test where you'd be looking at a two-sided test where my alternative would be not equal to. And we'll come back to that in a second when we look at proportions. That's the main idea of a significance test. So let's sum that up. We address a specific claim about a population. We're looking at the curve as if that were true. We're using a normal curve and what we know about to either reject that claim, saying our sample is too far from that claim to be true, or fail to reject, meaning that we could have just had that p-hat occur by chance. Now we use it in order to determine if it could be due to chance variation, which is p-hat just isn't 0.5 but it's 0.52. Just like if I flip the coin 100 times, I might not get 50 heads, I might get 52, I might get 48. But if I got 5 heads, then I'd say, wow, it's not looking plausible that that's a fair coin. And that's the kind of thinking that we want to be going through when we're looking at significance tests. So chance variation, or we should reject our null hypothesis, it is not appearing to be true. So keep that in mind as we go forward. So this option, it's due to chance, so we would fail to reject our null hypothesis. I got 52% of my flips heads. The coin could be fair, which the proportion that we propose is 50% if it's fair. Second explanation, my p-hat my proportion is 5%, that's really far away, it's not plausible that I have a fair coin, I'd reject the null hypothesis that the coin is fair, that the proportion of heads is 50%. So this is how we represent the null hypothesis. It's a test designed to assess the strength of evidence against the null hypothesis. So we're looking to see we have evidence against it or we don't. So it's just like a court of law. We have evidence against the accused and they're guilty or they are not guilty. Nobody's found innocent. And here we're not saying if I got 52% heads, it doesn't prove that my coin is a fair coin. It just shows that it could be. Again, 52% isn't equal to 50%. It could have happened by chance. So we're not proving that it is 50%, even if I got 50% with my sample proportion, because that could have occurred by chance. This is often called the statement of no difference because it'll be the claim that the coin is fair and we're trying to prove against it. And then we represent the alternative hypothesis as H sub A. The state part of your problem, you'll start with a null hypothesis, the claim, oftentimes a statement of no difference we call it, and then the alternative hypothesis. Those hypotheses should express hopes or suspicions before we see data. We shouldn't be basing those on our data, or that wouldn't be solid science. So let's look at two kinds of one-sided hypothesis tests. Our null hypothesis here is the true proportion. Notice that this is p, not in terms of p hat. We're claiming that the true population proportion is 0.2. My alternative would be that it's greater than 0.2 here, and that would be we're looking for p hat to be far enough above 0.2 to show that 0.2 is not in fact true. If my alternative was less than 0.2, then I'd be looking on the lower half left here. And we'll define what plausibility is by using a symbol called alpha. Oftentimes we'll use 0.05, although that's somewhat arbitrary and just because people have done that in the past. Sometimes people use 0.01. That's up for debate on what plausibility is. However, before we conduct our significance test, we say what we're going to define as the rejection region, the area. So if it's 0.05, we're saying the area of the normal curve being 0.05 here. A two-sided test we might use if we don't have a suspicion about whether the true proportion is greater than or less than the hypothesis. We just don't think that the hypothesis maybe is true. So a two-sided, we use not equal sign. And that means that we'd be checking to see whether p hat is far enough above or below the hypothesis here of 0.2 in order to determine whether we can reject the null hypothesis. Now that's going to vary depending on sample size because that changes our standard error of our proportion. So these are going to depend upon sample size in order to determine the standard deviation that we'd be using. Value and the definition here, which is one that quite a few people struggle with. Assuming the null hypothesis is true, so that claim, we just looked at p equals 0.2 in the video, assume that that's true, what's the probability that our sample statistic, p hat if we're talking about proportions, or x bar if we're talking about sample means, would take a value as extreme or more extreme than the one actually observed? So if it's one-sided and our alternative hypothesis has a greater than symbol, what's the probability that p hat would be equal to or greater than it is? If the alternative is that it's less than, then we would look at what's the probability that p hat is equal to or less than what it is. So more extreme, we're looking at the whole side of the normal curve beyond p hat there. And if it's two-sided, we're looking at both sides, and we'll look at how that changes things. So the area under the normal curve beyond the sample statistic is the way to try to kind of grasp that, and looking at pictures oftentimes helps. The further away p hat is from the null hypothesis in terms of the standard deviation, the smaller the p-value is we'd get. Now again, think of it as a criminal trial. P hat is not proving a claim to be true, but it could give strong evidence against the claim. So the further it is, the stronger the evidence. Large p-values don't give convincing evidence because what we're saying is the claim could be true. However, they never prove the claim. They're just saying it could be true. We could have a slightly different answer due to chance. That claim could be true. We're not saying it is true. So we never accept the null hypothesis. We fail to reject it since the data are consistent with the null. They don't prove it. So small p-value, we reject the null, conclude the alternative. In the context of the problem means regarding whatever we're investigating. Large p-value, fail to reject, we cannot conclude the alternative. The result is statistically significant at an alpha level. Alpha, we're defining the level of plausibility, meaning the largest p-value where we would still reject. It's like the border of what it would be. We're saying if our p-value we get, or the likelihood of getting that sample statistic given that the null hypothesis is true, if our p-value is less than that alpha, then we would reject our null. That means it's far enough on the lower end of the normal curve or the high end of the normal curve to say that it's not plausible that the null hypothesis is true. Now, we oftentimes use 0.05 due to its use by one famous statistician. However, this is up for debate. Was just reading an article about how many people think we use it in science because it's taught, and we teach it because it's used. So it's a good question to say that's a 1 in 20 chance. Less than that's not plausible. It's kind of due to practice, but that's up in the air. Some medical studies also use a 1% chance for plausibility. So a small p-value, though, would say that it's less likely that a claim is true. It's less plausible. So significance level could vary depending on what we're looking at using, depending on the strength of the evidence we need. What happens when we're wrong in a significance test? A type 1 error is we reject the null when it is true. And a type 2 error is when we fail to reject the null when it's false. These lead us to the power of a test, which is one of the more challenging things to understand in this chapter. But it's the probability that the test will reject the null hypothesis at a chosen significance level when an alternative value of the parameter is true. So we'd have to always say, if this alternative is actually this, what's the likelihood that we'd reject it? We'll get into this more in class. So here are the outcomes. We could reject the null hypothesis or fail to reject. If we reject and it's actually true, we made the type 1 error. If it's false, then we made the correct conclusion. If we fail to reject and it's true, we made the correct conclusion. If we fail to reject the null hypothesis and it's actually false, we made a type 2 error. So that's the general idea, which is a lot to wrap your head around. Let's look at what it looks like for a sample proportion. So this is our state plan do conclude, where we state the hypothesis we're testing in the alternative, define the parameter mu or p. We plan by checking our conditions. We do the problem by calculating the test statistic in terms of z or t, depending on whether we're using a sample proportion or sample mean, and whether we know this population standard deviation. And we conclude by comparing the p-value to the alpha level. Also, we'll add the alpha level into the state portion. Conditions are much the same as we've gone over before, so we won't spend a long time on this. An unbiased estimator, the normal condition, and the independent condition. Now we'll use, since we're assuming the null hypothesis is true, for the normal condition we'll use the proportion from the null hypothesis. That's what this symbol indicates in order to test the normal condition. Our sample statistic, we're looking at to see how far our statistic p hat is from what's proposed in the null hypothesis in terms of the standard error of the statistic, based on the sample size. So that's how we calculate our z for a significance test. Response question, what is a p-value? What does it describe about the likelihood of our claim in terms of our sample statistic? And how are confidence intervals and significance tests similar, and how are they different? So pause now and answer that, and then we'll wrap up with a little bit of an explanation of a sample problem and your multiple choice. Okay, here's an example involving a mayoral election. Gina feels that she's confident she'll be elected by obtaining more than 50% of the vote. Our random sample of voters shows that 56 will vote for her. Should that justify her confidence? Meaning, does that prove she has a majority? So two possible explanations. At most, 50% of the voters support her, and we had this just due to sampling variability. We happen to pick more supporters in our SRS. And two, the sample proportion is above 50% because it reflects the true parameter. This represents our null hypothesis. This represents our alternative. So if 50% of the voters actually supported her, here's a simulation that represent values at 56% or sample proportion or greater. We can see that here that happened 13.75% of the time. So it's plausible that she got 56% by chance. It happens about 14% of the time. So she should not be confident in victory. That could have just happened by chance. If we looked at state plan do and conclude, we define the parameter. Our null hypothesis is that she's got 50%, or alternative that she hopes she can reject that null and say that she's got more than half. Here's the plan section, and I'd like you to pause right now and do this function on your calculator to get a sense of how to run this. The tail end of the problem and your multiple choice will be showing shortly.